In this lecture, we look at how currents create magnetic fields. We'll consider a current loop with the long sides parallel to the north. First, we lay out the wire, and we lay the long side parallel to the direction of Earth's north. There's no current flowing through this wire yet. And then we put two compasses on the two long sides of the wire, so that the red needle, which of the compass points north, parallel to the wire. When we turn on the current, we see that the needles of the compasses are deflected. The one on the right points to the right, the one on the left points to the left. The difference between the two is that the current in one case is flowing north, and whereas on the right hand side, on the left hand side, the current is flowing south. We'll see how that, in a second, see how that changes the deflection. If we were to look at the current of a single wire, we find out that the B field is circularly symmetric around the axis of the current carrying wire. If you did the experiment, which was done in a YouTube video by Paul Hewitt, which you can find at this website, there you see that the current is flowing through this large bar in the center of the picture, and all the compasses that are laying on the table there are arranged circularly around this bar, and you see the needles are pointing in a circular way around the bar, like shown in the diagram. The general rule is that if you put your thumb in the direction of the current, and your fingers curl in the direction of the magnetic field around the current carrying wire. So that if we go back to our simple circuit, if you point your thumb north and your fingers curl around the right-hand wire, you see that your fingers will be pointing to the right, deflecting the red needle to the right. If you point your thumb south, like on the left-hand wire, your fingers will curl around, and they're on top of the wire, they're pointing to the left, deflecting the needle to the left. Let's look at the magnetic field of a long current carrying wire in more detail. Consider a small piece of a current carrying wire. We see this blue wire with the current flowing through it. And a small piece of it is ds, which is indicated by the ds with a vector hat on top. The vector points in the direction of the current carrying wire for that small piece of wire. It's going to produce a small part of the magnetic field, dB, at point P where we like to measure it. There is a vector r which points from this element of wire to the point P. There is a law known as the Biot-Savart law, which is that gives the B field in terms of these quantities. The dB vector is equal to mu0 over 4 pi times the current times the cross product of ds and r divided by the magnitude cubed of the r vector. Mu0 is known as the permeability, and it's equal to 4 pi times 10 to the minus 7 teslas meters per amp. In general, if you're trying to figure out the magnetic field from the whole wire, the geometry makes it very complicated. But there are some simple cases where it is easier to figure it out. In which case, one of them is a long, very long, straight current carrying wire. So if we have a long wire, and we use the result ends up being the magnitude of this current carrying wire is equal to mu0 times the current divided by 2 pi divided by the magnitude of r, the radial distance from the wire to the point where the magnetic field is measured. The direction is again given by the right-hand rule, so that you put your thumb in the direction of the current, your fingers curl around the wire, so you get this circular pattern of the B field. Let's go ahead and try different values of these quantities. Let's hold the current fixed at 1 amp and change B and look at B for different values of the magnitude R, the distance from the wire. If we're 1 meter away from the wire, then the field is 2 times 10 to the minus 7th Tesla, very small. If we're about a centimeter away from the wire, the field grows to 2 times 10 to the minus 5th Tesla. And if we go all the way to within 2 millimeters of the wire, we get to 1 times 10 to the minus 4 Tesla, or which is about the strength of the Earth's magnetic field. So we're finally getting to something that a compass can see easily. So it's not a very strong field. Let's look at simple case 2 of a small loop with a radius r of a current carrying wire. So here's the little red loop here with an eye in it. The loop creates a field that looks like a bar magnet or dipole field. So it looks something like this, where you have these loops going out to the side. This produces like a north pole at the top and a south pole at the bottom, just like with a bar magnet. And of course the field is radially symmetric, as is seen by spinning this field. The magnetic field at the center of the loop, right at the center, is equal to mu0 times the current divided by 2 times the radius of the loop. The direction of the magnetic field at the center follows the right-hand rule as before. Curl your fingers in the direction of the current, and your thumb then points in the direction of the B field. For I is equal to 1 amp, what is B for different radius r? For 1 meter, a very big loop, then the magnetic field is 6.3 times 10 to the minus 7 Tesla. For 1 centimeter, the field is 6.3 times 10 to the minus 5th Tesla. For 0.06 meters, or 6 millimeters, we get to 1 times 10 to the minus 4 Tesla, or roughly Earth's magnetic field again. So still in this case, a 1 amp current through it has to be going through a relatively small loop to create a field similar to Earth's magnetic field. Our third simple case looks at a spiral of current carrying wire. This is known as a solenoid. It's shown below as a red spiral with a current flowing in it. And the solenoid creates a field that looks like a bar magnet or a dipole field, similar to that of a single loop of wire. The field lines are shown, and you can see that they have a dipole pattern, though they're a little bit stretched from the single loop. Again, there's a north and south pole, and again, it's symmetric around the axis of the solenoid. The magnetic field doesn't depend much on the position inside the solenoid. This can be seen by looking at the magnetic field lines inside the solenoid and seeing that they're nearly parallel. As a matter of fact, in the case where the solenoid is very long, then the field inside the solenoid does not depend on the parameters like the radius of the solenoid or the length of the solenoid. It depends simply on mu0, which is the permeability, times m, which is the number of turns per length, times the current. The direction of the magnetic field inside follows the right-hand rule as for the loop. So you curl your fingers in the direction of the current, and your thumb points in the direction of the B field. For a current of 1 amp, what is the magnitude of the B field for different values of the number of turns per length? For 10 turns per meter, the magnetic field is 1.3 times 10 to the minus 5 Tesla. If we increase the number of turns by a factor of 10 to 100 turns per meter, the magnetic field goes up by a factor of 10 to 1.3 times 10 to the minus 4 Tesla, which is about the strength of the Earth's magnetic field. If we increase the number of turns by a factor of 100 to 10,000 turns per meter, we're now getting to a value that's similar to a bar magnet, or 1.3 times 10 to the minus 2 Tesla. To review, we show the patterns given by our 3 different simple cases. Shown, there's a long straight wire and there's iron filings mapping out the fields. You can see the radial symmetry there. You can see the loop of wire, which has the dipole field, and there's a solenoid of coil of wire. You can see that the lines are very straight in the center, and then you see the dipole pattern coming out the ends. So there are three current configures for which you should know what the magnetic field looks like. This means being able to know the direction of the B field with respect to the current, proper use of the right-hand rule, and it also means you should know the functional form for these three simple cases.